All right, in this video we're going to look at a technique for taking antiderivatives called integration by substitution or antidifferentiation by substitution. Just as a reminder what an indefinite integral is, an indefinite integral is an integral that has no limits of integration. So when you're evaluating an indefinite integral, so there's no values there, we're not necessarily thinking about area at all, but we might note that the antiderivative of f prime of x is equal to, so it's going to be a function whose derivative is what's in the inside, and we know that they differ by constants. But again, we're not necessarily thinking of area, we are thinking of functions or families of functions whose derivative is the function in the inside. So it's just an example for this first case, if we're evaluating this indefinite integral, we're looking for the function or family of functions whose derivative is what we see here. And so with a little guessing and checking, I see an x to the fourth and a 1/2 would make that work, and then the antiderivative of cosine is sine. So that would be what we mean by evaluating that indefinite integral. Now, integration or antidifferentiation is a more difficult process than taking derivatives, as we'll see soon, so we'll need some techniques. But just notice that, we've taken derivatives. So for instance, if we took the derivative of tangent here, the derivative of tangent is secant squared, so it would be secant squared of what's in the inside, e to the 4x squared. And then by the chain rule, it's the derivative of e to the 4x squared, which is e to the 4x squared times the derivative of 4x squared, which is 8x. So if we clean that all up, we might write it as 8x e to the 4x squared times secant squared of e to the 4x squared. So it's kind of this crazy derivative here. And notice down below, if I asked you to take the antiderivative of this function, you should notice that it's precisely what we see above. And so I'm literally just undoing this process, and I'm going to write down its antiderivative, which is what we see here, plus a c. So all that's fine, especially since I sort of primed you here, right? I had you take this derivative, and then I just immediately had you do an antiderivative. But the question is, how could we successfully do a problem like this, when we're not primed as we were above, right? We just took its derivative, so we recognized it. But are there techniques we can use to make the process a little easier? And there is. One's called substitution. So substitution, the integration by substitution, or antidifferentiation by substitution, it undoes the chain rule. So substitution undoes the chain rule. I'm just going to kind of note that and show you what I mean. Substitution undoes the chain rule. So in all the examples you'll see in which we're using U-Substitution, essentially what we're going to be presented with is an example that has this form. All right, so let me just kind of indicate the structure of what this looks like. So say you had an integral that can be thought of as f prime of g of x times g prime of x. What you should notice is, so you've got this g of x, and then you have its derivative, both present within the integral. That is a situation in which substitution will work very well. And so this is what it'll look like. We want this to be a little more presentable, a little more obvious than what it looks like now. So what I'm going to do is I'm going to go over here and say I'm going to call u. U tends to be the letter that's conventionally used, but it can be any letter. Let u be g of x. And then we're going to take the derivative, and we use differential notations. I'm going to write du equals g prime of x dx. Okay, it's like I said before in a different unit. Du dx equals g prime of x, but you can separate the differentials to make it look like this. And this is actually really helpful because now what I'm going to do is I'm going to replace my g of x with just a u. Try to get my colors here, right? That is going to get substituted with a u, and then g prime of x dx is going to get replaced with, like that there. All that can be substituted with a du. And that'll leave a very obvious indefinite integral. So making those substitutions, this becomes f prime of u. And then remember, all of this is just du. And so now it's just asking me what the antiderivative of f prime of u is, but that's just f of u plus c. And then, of course, you go back and note what was really in the location of the, right? What was u standing for? It was a standing for g of x. So your final answer would be f of g of x plus c. So all substitution problems tend to have that structure. All right, and again, notice above here, right? I have exactly what we see down here below. All right, so we'll do a couple examples, and then we'll do more examples in a different video. So let's start with some straightforward ones. Right, let's say you had to evaluate this indefinite integral. So, of course, you could always just do some guessing and checking. There's actually nothing wrong with that, especially if you have success doing guessing and checking. You know, don't use any technique if you can just write down an answer and check it. But let's say you don't know initially what to do. You could try using U-Substitution. So I see an x squared plus 1, and then I see 2x, which is the derivative of that. So I'm going to try letting u be x squared plus 1. And then I'm going to take the derivative, and I'm going to represent that as du. So du equals 2x dx. And this is going to be a perfect substitution because my du gets to replace this, and my x squared plus 1 gets to replace this, and I'll be left with a much more manageable indefinite integral. So I'm going to write, rather than x squared plus 1, it's now just u to the 12th, and then 2x dx can just be replaced with a du. Now I've made this problem in terms of u, so the antiderivative of u to the 12th is u to the 13th, and then a 1/13th plus a c, and then just go back and replace what the u really was. It was really x squared plus 1. So it's really 1/13th x squared plus 1 to the 13th plus c. So we've kind of used this substitution as a vehicle to make a somewhat less obvious indefinite integral into one that was much more obvious, right? U to the 12th is a pretty straightforward antiderivative to take. Let's try one more, and then we'll do different examples in another video. All right, so this says to evaluate 3x cubed sine of 2x to the 4th plus 1. And we need to use U-Substitution. Pattern recognition is just, I think, a fancy term for guessing and checking. So the first thing to notice is I see this 2x to the 4th plus 1. Now the derivative of 2x to the 4th is 8x cubed. This isn't exactly 8x cubed, but that's okay as long as there's an x cubed. That 3, and the fact that that's a 3 and not an 8 is not a problem. Constants can always be sort of dealt with. So the key is if you see a function in some multiple of its derivative, or some version of its derivative. So let me just kind of note that u sub works when you see a function and some multiple. So I'll kind of use this informal word, version/multiple of its derivative. And I'm using the term multiple loosely. I just mean basically any constant that can be, scaled up or down to be the appropriate substitution. So note what happens here. I'm going to let u be 2x to the 4th plus 1 And then du becomes 8x cubed dx. Now, my 2x to the fourth is taken care of. That's just going to be u. And 3x cubed dx, that's not quite what I have over here, right? I have 8x cubed dx. So people have different styles. What I tend to do is I'm just going to ignore that 3. That 3 can be factored out. It can be kind of put off to the side, and it'll combine with whatever it needs to combine with. But x cubed dx can be substituted, right? I can get this by itself. So I often have to do a little step here and just say, all right, well, du divided by 8 is x cubed dx. And now I have a perfect substitution that I can use, or that I can make. So let's see what happens here. This becomes, so this is what I'll do. I would take a 3 out, take that 3 out. X cubed dx, okay, it doesn't matter if they're all split. Think of this as all being multiplied. X cubed dx is now just du over 8. Okay, du over 8. And I have sine of the thing that I'm calling a u. So all in all, du over 8 is what's in blue. So I might just put a 1/8 here. Okay, I sort of split that up. I can even take the 1/8 out and represent it like this. But the point is, what you're left with is a much more straightforward and indefinite integral. So the antiderivative of sine of u is negative cosine of u plus c. So this becomes negative 3/8 cosine, and we replace the u with what it really was, which was 2x to the fourth plus 1. If you go back and trace our steps, right, I'm going to replace that with 2x to the fourth plus 1. And there is my antiderivative of 3x cubed sine 2x to the fourth plus 1. All right, so there's an intro to U-substitution and a few examples. We'll do a few more in another video.